The National Electrical Code, referred to as the NEC, does not contain specific requirements for minimum spacing or bonding between lightning rod conductors and electrical conductors. However, it does make a reference to the IEEE Institute of Electrical and Electronics Engineers and NFPA 780-2017 standard for the installation of lightning protection systems. According to IEEE and NFPA 780-2017, the following recommendations should be followed. Firstly, separation. Lightning rod conductors should be separated from electrical conductors by a minimum of 12 inches, or 305 millimeters. Secondly, bonding. If the required separation distance cannot be maintained, the lightning rod system and the electrical system should be bonded together at the entrance to the structure or at the point of closest approach. The bonding conductor should be sized appropriately to handle the maximum fault current that the electrical system can produce. Considering the Canadian Electrical Code, or SEC, a minimum separation of 2 meters, which is approximately 6.5 feet, is required between lightning rod conductors and electrical conductors. If this is not possible, the ground electrodes for both systems must be bonded together. Concerning a toll booth project, and to address whether electrical conductors and the roof of the toll booth are within the required separation distance from the lightning rod conductors. If they are not, the project should be modified to meet either the NEC or CC requirements. If following the NEC requirements, bond the lightning rod system and electrical system together at the entrance to the structure. If following CC requirements, provide a 2-meter separation or bond the ground electrodes. If bonding is required, it should be performed at the point of closest approach between the lightning rod conductors and electrical conductors. Typically, this is at the entrance to the structure where the conductors enter the building. Looking further into the details of lightning protection systems, understanding the principles and practices can help to ensure safety and compliance. Lightning protection systems are designed to protect structures from damage due to lightning strikes. These systems provide a low resistance path for lightning current to flow to the ground, thereby preventing the current from passing through the structure and causing fire, explosion, or electrical damage. The key components of a lightning protection system are air terminals, conductors, and grounding electrodes. Air terminals, often referred to as lightning rods, are installed on the roof of a building to intercept lightning strikes. These terminals are typically made of copper or aluminum and are designed to provide a preferred point of contact for lightning. Conductors are used to connect the air terminals to the grounding electrodes. These conductors must be of sufficient size to carry the large currents associated with lightning strikes. Copper or aluminum conductors are commonly used, and they should be installed in a way that minimizes bends and sharp turns, which can increase impedance and reduce the effectiveness of the system. Grounding electrodes are installed in the ground to provide a path for the lightning current to dissipate into the earth. These electrodes can be ground rods, ground plates, or ground loops. The NEC and IEEE/NFPA 780 provide detailed requirements for the installation and sizing of grounding electrodes. The separation distance between lightning protection system conductors and electrical conductors is a critical factor in preventing side flashes and ensuring the effectiveness of the lightning protection system. Side flashes occur when lightning current jumps from the lightning protection system to nearby electrical conductors, which can damage electrical equipment and create a safety hazard. As previously mentioned, IEEE/NFPA 780 recommends a minimum separation distance of 12 inches between lightning rod conductors and electrical conductors. The Canadian Electrical Code requires a larger separation distance of 2 meters. If these separation distances cannot be maintained, bonding is required to equalize the potential between the lightning protection system and the electrical system. Bonding involves connecting the lightning protection system and the electrical system together with a conductor of sufficient size to carry the fault current. This connection prevents voltage differences from developing between the two systems, which reduces the risk of side flashes. The location of the bonding connection is also important. The connection should be made at the point of closest approach between the lightning protection system conductors and the electrical conductors, or at the entrance to the structure. This minimizes the length of the unbonded conductors and reduces the potential for side flashes. In the context of a toll booth project, it is important to carefully consider the proximity of the electrical conductors and the roof to the lightning rod conductors. If the separation distance is less than the minimum required by the NEC, IEEE/NFPA 780, or SIC, bonding should be implemented. The bonding conductor should be sized according to the maximum fault current that the electrical system can produce. The bonding connection should be made at the point where the electrical conductors enter the building or at the closest point between the lightning protection conductors and the electrical conductors. In addition to bonding, other measures can be taken to minimize the risk of side flashes. These include using shielded cables for the electrical conductors, routing the electrical conductors away from the lightning protection conductors, and installing surge protective devices, or SPDs, on the electrical system. SPD are designed to protect electrical equipment from voltage surges caused by lightning strikes or other electrical disturbances. They are installed in parallel with the electrical equipment and divert the surge current to ground, thereby protecting the equipment from damage. Regular inspection and maintenance of the lightning protection system is also important to ensure its continued effectiveness. The system should be inspected annually by a qualified lightning protection contractor to identify any damage or deterioration. Any damaged or deteriorated component should be repaired or replaced promptly. In summary, lightning protection systems are designed to protect structures from damage due to lightning strikes. The NEC and IEEE/NFPA 780 provide detailed requirements for the design, installation, and maintenance of these systems. Separation distance between lightning protection system conductors and electrical conductors is a critical factor in preventing side flashes. If the required separation distance cannot be maintained, bonding should be implemented. In the context of a toll booth project, it is important to carefully consider the proximity of the electrical conductors and the roof to the lightning rod conductors and to implement appropriate bonding measures to ensure safety and compliance. Moreover, it is important to be aware of the specific requirements of the Canadian Electrical Code, as it has more stringent separation requirements than the NEC and IEEE/NFPA 780. If working on a project that spans the Canada-US border, it is essential to comply with the electrical codes of both countries to ensure the safety and effectiveness of the lightning protection system. Considering other aspects of electrical safety in and around structures, it is worth delving into grounding and bonding techniques more broadly. Grounding refers to connecting the electrical system to the earth, which provides a low impedance path for fault current to flow back to the source. This helps to protect people from electric shock and to prevent damage to electrical equipment. Bonding refers to connecting together all of the metal parts of an electrical system, such as the metal conduits, enclosures, and equipment grounding conductors. This creates an equipotential plane, which minimizes the voltage differences between different metal parts and reduces the risk of electric shock. The NEC provides detailed requirements for grounding and bonding in Article 250. These requirements cover a wide range of topics, including the sizing of grounding and bonding conductors, the types of grounding electrodes that are permitted, and the methods for connecting grounding and bonding conductors. The grounding electrode system typically consists of one or more grounding electrodes that are connected together to form a low impedance path to earth. Common types of grounding electrodes include ground rods, ground plates, and metal underground water pipes. The size and type of grounding electrode required depends on the size of the electrical system and the soil conditions. The grounding electrode conductor, or GEC, connects the grounding electrode to the electrical system. The GEC must be sized according to the size of the service entrance conductors. The equipment grounding conductor, or EC, connects the metal parts of the electrical system to the grounding electrode. The EGC must be sized according to the size of the overcurrent protective device protecting the circuit. In addition to grounding and bonding, surge protection is another important aspect of electrical safety. Surge protective devices, or SPDs, are used to protect electrical equipment from voltage surges caused by lightning strikes, power line switching, and other electrical disturbances. SPD are installed in parallel with the electrical equipment and divert the surge current to ground, thereby protecting the equipment from damage. There are different types of SPD available, each designed for different applications. Type 1 SPD are installed at the service entrance to protect the entire electrical system. Type 2 SPD are installed at distribution panels to protect branch circuits. Type 3 SPD are installed at the point of use to protect individual pieces of equipment. The selection of the appropriate SPD depends on the voltage, current, and surge withstand capability of the electrical equipment being protected. Regular inspection and maintenance of the electrical system is also important to ensure its continued safety and reliability. The electrical system should be inspected periodically by a qualified electrician to identify any potential hazards, such as loose connections, damaged wiring, or overloaded circuits. Any identified hazards should be repaired promptly to prevent electrical shock or fire. Moreover, consider arc fault circuit interrupters, or FSIs, are another important safety device that are used to protect against electrical fires. FSIs are designed to detect arc faults, which are dangerous electrical conditions that can cause fires. When an arc fault is detected, the FSI trips the circuit breaker, interrupting the flow of electricity and preventing a fire. FSIs are required in many areas of the home, such as bedrooms, living rooms, and dining rooms. Finally, ground fault circuit interrupters, or GFCIs, are another important safety device that are used to protect against electric shock. GFCIs are designed to detect ground faults, which occur where electricity flows through an unintended path to ground, such as through a person's body. When a ground fault is detected, the GFCI trips the circuit breaker, interrupting the flow of electricity and preventing electric shock. GFCIs are required in areas where there is a risk of exposure to water, such as bathrooms, kitchens, and outdoor areas. In summary, electrical safety is a critical aspect of building design and construction. Grounding, bonding, surge protection, FSIs, and GFCIs are all important safety measures that help to protect people from electric shock and to prevent electrical fires. Regular inspection and maintenance of the electrical system is also essential to ensure its continued safety and reliability. The NEC provides detailed requirements for electrical safety, and it is important to comply with these requirements to ensure the safety of building occupants. Regarding lightning protection systems, it's also vital to understand the concept of the zone of protection. The zone of protection is the area around the lightning rod or air terminal that is considered to be protected from direct lightning strikes. The size and shape of the zone of protection depends on the height and location of the air terminal. There are several methods for determining the zone of protection, including the rolling sphere method and the angle of protection method. The rolling sphere method involves imagining a sphere with a specific radius rolling over the structure. The areas that are touched by the sphere are considered to be unprotected, while the areas that are not touched by the sphere are considered to be protected. The angle of protection method involves drawing an angle from the tip of the air terminal to the ground. The area within this angle is considered to be protected. The NEC and IEEE/NFPA 780 provide guidance on the selection of the appropriate method for determining the zone of protection. It is important to ensure that all parts of the structure are within the zone of protection of at least one air terminal. If necessary, additional air terminals should be installed to provide adequate coverage. The material selection for lightning protection components is also a critical consideration. Copper and aluminum are the most common materials used for air terminals, conductors, and grounding electrodes. Both materials have excellent electrical conductivity and corrosion resistance. However, copper is generally preferred for grounding electrodes because it is more resistant to corrosion in soil. Aluminum is often used for air terminals and conductors because it is lighter and less expensive than copper. When using dissimilar metals in a lightning protection system, it is important to take precautions to prevent galvanic corrosion. Galvanic corrosion occurs when two dissimilar metals are in contact in the presence of an electrolyte, such as water or soil. The more active metal will corrode, while the less active metal will be protected. To prevent galvanic corrosion, it is important to use compatible materials or to isolate the dissimilar metals from each other. For example, when connecting aluminum conductors to copper grounding electrodes, a bimetallic connector should be used to prevent galvanic corrosion. In addition to the technical aspects of lightning protection systems, it is also important to consider the aesthetic impact of the system. Lightning protection systems can be visually obtrusive, especially on historic buildings. There are several ways to minimize the aesthetic impact of lightning protection systems, such as using concealed conductors, painting the components to match the building, and using decorative air terminals. It is also important to involve architects and historic preservation consultants in the design of the lightning protection system to ensure that it is compatible with the building's architecture and historic character. Finally, worker safety during the installation and maintenance of lightning protection systems is paramount. Lightning protection work should only be performed by qualified and experienced contractors who are familiar with the safety requirement. Workers should wear appropriate personal protective equipment, such as safety glasses, gloves, and hard hats. They should also be trained in the proper use of tools and equipment. When working on roofs, workers should use fall protection equipment, such as safety harnesses and lifelines. They should also be aware of the potential hazards of working near electrical power lines and take precautions to avoid contact with these lines. In conclusion, lightning protection systems are complex and critical safety features that require careful design, installation, and maintenance. Understanding the technical aspects of these systems, as well as the relevant codes and standards, is essential for ensuring the safety of buildings and their occupants. Attention to detail, proper material selection, and adherence to safety procedures are all crucial for successful lightning protection projects.